In this video, we're going to talk about rational equations, and we can really think of this as just an upgrade from quadratic equations because we're going to use a lot of similar methods. A rational equation is any kind of an equation that contains rational expressions. For instance, what if I had x cubed plus 3x squared divided by x squared minus 2x minus 15 equals 4x plus 5 divided by x minus 5. So this section does give a nice conclusion to chapter 1, which really is all about combining a lot of core ideas that we've seen. We've seen how to work with rational expressions, and we've seen how to solve quadratic equations. So the core strategy will be the following. We want to try to see if we can transform this rational equation into a polynomial equation. And we're going to start doing this by factoring as much as we can and searching for cancellations. We also know that with rational expressions, we need to pay attention to restricted values, but we typically reserve that step to the very end. So first, let's factor the left and the right-hand side of the equation. The left-hand side numerator factors with the GCF method, and the denominator factors with the AC method. The right-hand side, however, doesn't factor at all. But I can automatically see that I have, on the left-hand side, 2 copies of x plus 3 in the numerator and denominator. So I can go ahead and cancel those out. And what I'm going to get as a result is x squared divided by x minus 5 equals to 4x plus 5 divided by x minus 5. To turn this into a polynomial equation, I'm going to multiply both sides of the equation by both denominators that I see. But for us, I have the same denominator in both cases. So I'm just going to multiply both sides by the quantity x minus 5 so that it cancels out and leaves me with the quadratic equation x squared equals to 4x plus 5. Now we're just in a section 1.8 case. I'm going to take this and write it in standard form. I'm going to notice that it factors into x minus 5 times x plus 1, and this is going to give me the solutions of x equals to 5 and x equals to negative 1. So, by simplifying our rational expression and then multiplying both sides by the present denominators so that we can get a quadratic equation is what allows us to solve for x. However, there's one more thing we got to pay attention to. Rational expressions yield restricted values. This means I need to look at every factor that is or was in the denominator at some point. When I do that, I'll see that I have restricted values of 5 and negative 3. Now let's compare these restricted values with our solutions. Notice that we actually have a conflict. 5 is both a solution and a restricted value. Basically, this means that 5 cannot be a solution because 5 has been outlawed. So one of the reasons that we learned to check rational expressions for restricted values is to see that if any of our restricted values conflict with the solutions that we find. So even though the quadratic equation x squared minus 4x minus 5 equals to 0 has 5 and negative 1 as a solution, the original rational expression has 5 as a restricted value, so we must rule it out. Therefore, we have exactly one solution of x equals to negative 1. So at the end of the day, we solve a rational equation by turning it into a polynomial equation. And then we just have to check if any of the solutions that we find have conflict with our restricted values. For our next example, we're going to solve the equation 3x squared over 5x minus 1 equals to 0. The form that we want is to have one term on each side. So we're going to start by taking this negative 1 and moving it to the right-hand side. To be a little bit more clear, we simply just want to make sure that we have one term on the left-hand side and one term on the right. So making this happen could look differently for each problem. For us, I just had to take that negative 1 and move it to the right-hand side. For other problems, I might need to combine fractions, but I'm aiming for one term per side. Since nothing is going to cancel out, I'm going to go ahead and multiply both sides by the only denominator that I see, which is 5x minus 1. Once I carry out this multiplication, I'm going to get a cancellation on the left, and that term is going to stack up on the right. This will result in the quadratic equation 3x squared equals 5x minus 1. And just like before, I'm going to put this into standard form and take a look at what I've got. This is a quadratic equation for which the AC method fails. So we are going to use the quadratic formula. Our A value is 3, our B value is negative 5, and our C value is 1. Plugging all those values into the quadratic formula gives us the following. As we simplify, we get 5 plus minus the square root of 25 minus 12 divided by 6, which turns into 5 plus minus the square root of 13 divided by 6. Now that we have our solutions, let's check restricted values. The only denominator in this whole problem was 5x minus 1. If we set that equal to 0 and solve, we get x equals to 1 over 5. However, our solutions are definitely going to be a decimal number, and 5 plus minus the square root of 13 over 6 is definitely not numerically the same as 1 over 5. So, this problem has two solutions, and our restricted values do not rule either of our solutions out. For our last case, what happens if I have the following kind of equation? Absolute value of 2x plus 1 over 3 minus 1 over x plus 1. Like I said, section 1.9 showcases a lot of combinations of the ideas that we've learned. We have an absolute value expression and a rational expression, but we can handle this. First and foremost, remember that we have a strategy. We want to make sure that we get one term per side of the equation. So let's take 1 over x plus 1 and add it to the other side. This is going to give us the equation absolute value of 2x plus 1 divided by 3 equals 1 over x plus 1. I'm going to multiply both sides by 3 so that I have the absolute value term on its own side of the equation. So I have the absolute value of 2x plus 1 equals 3 divided by x plus 1. We said in the last slide that we want to try to reduce this to a polynomial equation, and eventually we do, but right now that absolute value term is kind of taking priority. Because I have absolute value of stuff equals to something else, I'm now going to use the methods that we learned previously to split this into two separate equations. I'm going to get 2x plus 1 equals to negative 3 over x plus 1, and 2x plus 1 equals to positive 3 over x plus 1. Remember that whenever I have absolute value of stuff equals to a number, I set the quantity inside the absolute value bars equal to the positive and negative version of whatever that number was. The idea still works when my right-hand side is a rational expression. I set 2x plus 1 equal to the positive and negative version of 3 over x plus 1. This is the part where I can move forward. I now have two rational equations that I need to solve, and that's fine. It might just take a little bit more work, but this is still doable. I now can rely on the idea of turning our rational equations into polynomial equations. Starting with the equation on the left, I'm going to multiply both sides by x plus 1. This is going to give me x plus 2 times 2x plus 1 equals to negative 3. Foiling this out and writing it in standard form will land me at the equation 2x squared plus 3x plus 4 equals to 0. The AC method fails here, so I need to rely on the quadratic formula to get the following solutions. Here I have imaginary solutions, so that first rational equation does not give me any real solutions. Let's move on to the next. For the equation on the right, I'll again multiply both sides by x plus 1. When I FOIL this out and write it in standard form, I get the equation 2x squared plus 3x minus 2 is equal to 0. This quadratic factors with the AC method, and when I use my zero product property, I'll find solutions of x equals to 1/2 and negative 2. The only thing I have left to do is check for restricted values. Since x plus 1 was the only denominator factor, we only get one restricted value of x equals to negative 1. But thankfully this value does not conflict with any of the real or the imaginary solutions that we found. So nothing gets ruled out. We have two imaginary solutions and two real solutions of 1/2 and negative 2, and we're done.